Hello, and welcome to video 6.2.1 on entropy and free energy. Okay, so let's go ahead and talk about standard state before we talk about entropy. Thermodynamic quantities are generally reported at standard state. So what is standard state? That's when all aqueous substances in both reactants and products are at a 1 molar concentration. And gaseous substances have a partial pressure of 1 bar, which is about 1 atmosphere, and usually at 25 degrees Celsius or 298 degrees Kelvin. In other words, for reversible reactions, Q is equal to 1. That means we're going to be at equilibrium there. Quantities at standard state are denoted by naught, or sometimes you'll see a little bar through them. So as the change in enthalpy naught, right, delta H naught, S naught, delta G naught, and we'll see what that is in just a second, and E naught. So going into entropy. Now, what is entropy? I like to think of entropy just as a measure of disorder. You can think of your room. So if your room is super clean, it has very low entropy. If your room is super messy, it has very high entropy. So entropy is denoted S. That's a measure of the dispersion of matter and energy, which can just be described in 2 ways. 1, the number of arrangements of particles, or 2, the disorder of a system. Its units are joules over moles times Kelvin. Now, the absolute entropy is denoted S, and that describes the entropy of 1 mole of a substance, and usually you can look that up in a table somewhere. More complex substances have larger values of S, because the more complex something is, the more disordered it's going to be. However, we usually don't really care about just S. Usually we care about the change in S, because that's going to tell us more about how a reaction proceeds, or whether or not it's going to proceed at all. So, excuse me, when delta S is greater than 0, entropy will be increasing. The system becomes more disorderly. It gets more crazy. When delta S is less than 0, entropy decreases. The system becomes less disorderly, or more orderly, we can think of. Now, the value of delta S can be found in 2 ways. You can do products minus reactants. So remember, this is the sum. So all the products minus all the reactants. Or we can use Hess's law, depending on what we're given. So those are all for calculations. Now, what if you just wanted to look at a reaction and see if it's going to produce, if the entropy is going to increase or decrease? Well, you'd look at these 6 clues. If you have the temperature of a system going up, you're going to have more entropy. If we increase the volume of a gas sample, more entropy. If we increase the moles of the substance, just the overall moles in a reaction, we have more entropy. So if we look over here, 2 O3s go to 3 O2s, 2 to 3, right? The number of moles is increasing, more entropy. If we increase the number of substances in a reaction overall, we're going to have more entropy. We have 1 substance here in the reactants and 2 in the products. Entropy goes up. If we change states from more ordered to less ordered, so from solid to liquid, or liquid to gas, or solid to gas, all of those are going to increase our entropy. And here we have like an ice cube melting, right? So that's going to increase our entropy. A key here is to look for reactions that produce more moles of gas substances. More moles of gas usually means more disorder. So changing from a pure substance to a mixture is also more disorderly. So your entropy is going to increase. So here you're introducing waters, you're getting aqueous right here. And then we're getting, in a mixture, things are more disorderly. They're all mixed up. So again, our entropy is going to increase. Okay, following these 6 clues, I would like you to please pause the video and do example 1. So complete A, B, C, and D, and then come back when you're ready to see the answers. Okay, welcome back. So for part A, the delta S of the reaction is greater than 0. That means entropy is increasing because you're forming a gas. So we have and also really because you have more substances, right? So you're going from your solid to your solid plus your gas. So in a couple ways there, you're increasing entropy. And we're just going to say because the reaction forms a gas. Okay, for part B, delta S is going to be less than 0. Entropy is going to be going down because your system here is going from a gas to a solid. So you're getting way more ordered, right? Going from gas to solid. Okay, part C, delta S is going to be less than 0. And that's because if you look at the products, there are fewer moles than in the reactants, right? The products have fewer moles of gas rather than the reactants. So if we look at the reactants, we have 1, 2, 3 moles of gas. In the products, we have 1 mole of gas. This is a liquid. It doesn't count. Okay, and then part D, your delta S here is going to be greater than 0. Entropy is going to be increasing because the products have more moles overall and more moles of gas than the reactants. So we'll do and overall. Okay, so we can kind of see how that works now. Let's do a calculation and calculate our entropy. So consider the reaction 2SO2 gas plus oxygen goes to 2SO3 gas. Everything's gaseous. Predict whether delta S naught will be positive or negative. Remember, this is at standard state, right? So we're just going to assume standard state unless we're told otherwise always with these. So right now, I would like you to pause the video and work on part A and B. Predict whether it's going to be positive or negative. You'll be able to tell that just from the reaction, kind of like we did above. And then calculate the value of delta S using the values in their absolute entropy here. All right, so welcome back. So for part A, our delta S naught is going to be less than 0. And that's because our products have fewer moles of gas than our reactants. So we have 2 moles of gas in the products and we have 3 in the reactants. So our entropy here is going to decrease. Now for our calculation, calculate the value of delta S naught using the values of the absolute entropy. So we're just going to sum the products and subtract the reactants. So delta S naught equals, so I'm going to do brackets here just to kind of keep everything in order. So we have 2 moles, 2 times the value for SO3 minus 2 times the value for SO2 oops, that shouldn't be there, let's do plus sign, plus 1 times the value of, hold on, erase that. There we go. 1 times O2. And brackets. All right. So plugging in our values, and I'm just going to read from this table, delta S equals 2 times 257 minus 2 times 248 plus 1 times 205. Notice here that for a pure substance, our values are not equal to 0 when we're talking entropy. There's always some entropy in a system. Okay, so plugging all that into your calculator, delta S naught equals negative 187 joules per Kelvin. Okay, oh, joules per mole times Kelvin, rather. So, for this reaction, again, we see that we have a negative value. And again, that's because the products have fewer moles of gas than the reactants. Okay, that is it for video 6.2.1. I'll see you in just a bit for video 6.2.2.